derivative for a logarithm. So the way I say it in English is derivative of inside over inside. Every logarithm derivative is derivative of inside over inside. Yeah. Number 15. Decimal confusion problem. dx of ln of x. And natural log inside natural log. This is one of those problems that's just there to see if you can muddle through it, right? ln of ln x. Sometimes they put an extra ln in there, there's 3 of them, make it look all silly. All right, ln ln x. So when you differentiate the outer, sorry, what's the domain? Sorry about that. What's the domain? What do you have to guarantee? You have to guarantee that the inner function is what? Greater than 0. So now where is ln x greater than 0? I'm trying to remember the picture I drew. Think about the picture. Greater than 0 means above x-axis, right? When the function is greater than 0, it means it's above the x-axis. The x-intercept for the logarithm is at 1, right? Remember a second ago? I'm just going from the picture. I'm not really doing any analysis. There's 1. So the graph, right? It's above the x-axis here. And it just keeps getting bigger, right? Yeah. Right. So as long as x is bigger than 1, then my graph of ln is above the x-axis. That's greater than 0, right? Positive height values. So as long as x is greater than 1, ln of x will be greater than 0. And now if you put anything, right, that's greater than 1 into here, then you're putting something that's bigger than 0 into here, right, altogether, and that'll be fine for this one. That make sense? Not at all. Yeah?
Can you say that again really quick?
Yeah. To guarantee, to find your domain, you have to make sure that whatever you put here, whatever this ln x, it must be greater than 0, right? Okay. So if ln x is greater than 0, that means x is forced to be something in particular. What in particular? Well, for ln to be greater than 0, to be above the x-axis, you have to be beyond the value 1 for x. Okay? And it's just a chain. You're just saying, well, if x is bigger than 1, then ln x is bigger than 0. And if ln x will be bigger than 0, if I put it in here, it's positive, and that's fine for this ln, which is what we were worried about. So our domain is going to be what? 1 to infinity. All right. Derivative time. What's the first part of this chain rule? Derivative of outer function. 1 on x, but I keep the inner the same. So it must be 1 over ln. 1 over ln.
1x?
Times the derivative.
Times derivative of ln x, which is 1 over x. So 1 over ln x times 1 over x. So 1 over x ln x. Okay? You guys getting the hang of this ln stuff? I feel like I'm beating a dead horse now. Well, this is like the most problems we've ever done on any particular type of thing, I feel.
I thought you said that 1 over ln x was 1 over x.
The derivative, what's that? The derivative of ln x is 1 over x.
Oh, because you're keeping the first one the same, right?
Right, it's 1 over whatever's inside. The first part, right?
Yeah.
The first part of the chain rule for natural log is always 1 over whatever's inside. So 1 over this thing. Now I'm going to take the derivative of that thing, of the inside. That happens to be a 1 on x expression, not 1 on lambda. Okay, I just want to do a couple of the, actually really just 1 or 2, I guess a couple after all. A couple exponential function derivatives, more general cases than e, and then we're going to do some more complicated derivative techniques using exponentials and natural logs. These are the basic ones. Number 18 and number 19. Y equals 4 to the negative x sine x. 4 to the negative x sine x. Number 19. We'll move on to something a little trickier. X cubed times 3. And then then y equals x cubed times 3 to the x. Oh, look how funny these guys are. Look at see that? What do they do? Oh, look, power function, I switched up the rule, right? Base is x, exponent 3, base is 3, exponent is x, right? Isn't that cute? That's how sappy a mathematician is. I think that's cute or something. So now, dy dx up here, what is the most outer thing happening to this function? The product